Okay, today we're going to talk about the area and the definite integral and how they're related. So let's look at an example. I'd like to approximate the area between the graph of f of x equal x squared and the x-axis between x equal 1 and x equal 4 using L3, R3, M3, and T sub 3. All right, so first, I guess we should probably draw a picture. Y equal x squared. And we're interested in the interval from x equals 1 to 4. We'll put some labels on this. That's 16 and that's 1, etc. Okay, so our first calculation is we're going to do L3. L3 means we're going to approximate the area under this curve and above the x-axis from x equal 1 to 4 using 3 rectangles. Trying to approximate all this area using 3 rectangles, and the height of the rectangles will be determined by the left subinterval. So 3 intervals splits this into rectangles of width 1. So what I'm going to do is make my first rectangle go right to there. So notice the height of the rectangle is the left-hand side of that subinterval. And then the next one will go from 2 to 3. And I'll go up to my function at 2, and that'll be the height. And then my third one will be between 3 and 4, and go up to the function at 3. Go over like that. So the calculations are going to be the height, which is f of 1, times the width, which is 1, plus the height of the second one, which is f of 2, times the width, which is also 1, plus the height of the third one, which is f of 3, times its width. For Riemann sums, we usually have subintervals all of the same width, although they don't have to be. All right, so f of 1 would be 1, f of 2 is going to be 4, and f of 3 is going to be 9. So that gives us an approximation that the area under this curve and above the x-axis is approximately 14 square units. Okay, let's do another one now. Let's do the r sub 3. Similar calculation, except this time, instead of using the left side of the subinterval to define the heights of my rectangles, now we're going to use the right side. So between 1 and 2, we're going to go up to 2. As you can see, this is going to overestimate our area. So the area of the first rectangle will be the function at 2 times the height. Next rectangle will be the function evaluated at 3 times its width, plus the third rectangle will be f of 4 times its width of 1. Well, 2 and 3 we already have, so that's the 4 and the 9, but now we're going to add a 16 instead of a 1, so that's going to give us 29. So that's approximating the area under the curve using 3 rectangles evaluated on the right endpoint of the subintervals. All right, the next one is going to be M3. And for the midpoint approximations, exactly as you would have guessed, what we're going to do is we're going to get the midpoint of the subinterval, and that'll define the height of each rectangle. And that seems like a better approximation than either the left or the right, and it is in most cases. So how do we calculate that? Well, what's the height going to be? The height is going to be f of the midpoint between the first subinterval 1 and 2. So we're going to do 1 plus 2 divided by 2. So it's the average of the x values of that subinterval. And then times the width, which once again is 1. The second rectangle will be the average between 2 and 3. The function evaluated there times the width. And finally, the third rectangle will be the average between x equals 3 and 4 times the width. So what's that going to give us? That's 3 halves squared is 9 fourths plus 5 halves, so that's 25 fourths. And then 49 fourths. So 34, 70, what's that, 83 fourths? Or 20.75 square units for a midpoint approximation. Notice that's in between the left and the right approximations of 14 and 29. All right, finally we're going to do the trapezoid approximation. Now the first 3 types were all rectangular approximations. The fourth type, the trapezoidal, technically is not what's referred to as a Riemann sum. The first 3 were all Riemann sums, rectangular approximations of area under a curve. So now we're going to try a trapezoid. And let me give you the visual on that. So for the trapezoid, what we're going to do, we're going to take these 2 points and connect them and make a trapezoid. And then for the next subinterval, another trapezoid. And for the last one, another trapezoid. If you remember the area of a trapezoid, 1/2 base 1 plus base 2 times the height. Now these trapezoids are sideways. We're used to seeing the parallel sides at the top and the bottom, but they're left and right sides here. So the h is actually going to be the width of our subintervals on that. And the bases are going to be our function evaluated at 1 and 2, and then at 2 and 3, and then at 3 and 4. So let's write this out. What are we going to have? We're going to have 1/2 base 1, which is going to be f of 1, plus base 2, which is f of 2, and then times the height, which is the width of the subinterval 1. And then the next trapezoid, the bases are f of 2 and f of 3, times the height, which is 1 again. And finally, the last trapezoid, f of 3 plus f of 4, times 1. Now, before I go ahead and do all these calculations, let's look at this for a minute and rearrange. I can factor 1/2 out of all of this. When I do that, what am I going to have? I'm going to have an f of 1 plus f of 2 plus another f of 2 plus f of 3, another f of 3, and one f of 4. And of course, let's just rearrange this because we can. And how about if I wrote it like this? You already see where I'm going with this. That's f of 1, f of 2, f of 3. We still have another f of 2. And another f of 3. And then we had one f of 4, which we haven't included yet. And look what we have. That looks kind of familiar. That looks like f of 1 plus f of 2 plus f of 3. That was our L3 approximation. and then f of 2 plus f of 3 plus f of 4. That was our right rectangular approximation. So this is telling us that the trapezoid is actually going to be the average of L3 and R3. And in general, that's the case. The trapezoidal approximation is going to be the average of the left and right rectangular approximations. And so for L3, we had 14, I believe it was, and for R3 was 29. 29, right? So 43 over 2 for our trapezoidal approximation, which, as a decimal, that would be 21.5, which was close to the midpoint approximation. So there's the 4 most common ways of approximating the area under a curve. Okay, so now where are we going with this? So we're approximating area, and it's going to be the summation of f of x sub I times delta x. Delta x is the width of our subintervals. The area is going to be approximately that, unless if I keep increasing the number of subintervals, I'm getting better and better approximations, and then if I take the limit as those subintervals go to infinity, then I'm getting the actual area. Notice equals, and that's how we defined our integral as an area function. The integral from a to b of f of x dx gives us the exact area under a curve. Okay, so let's talk about some properties of definite integrals. If we switch our limits of integration, then that changes the sign of our answer. The integral from a to a, where a is a constant, of f of x dx is going to be 0. In terms of area, that means we're finding the area from a to a. There's no area under that curve between a and a. If we have the integral from a to b of a constant times a function, we can pull that constant outside of the integral and calculate the integral and then multiply by the constant at the end. We can split up functions within an integral. If we're doing an integral from a to b of one function plus or minus another function, we can separate those and do the integral separately and then add or subtract the two answers. Another very important property, if we're doing the integral from a to b of a function f of x dx, that will equal the integral from a to c plus the integral from c to b. All right, so let's take a look at just any kind of a function here. We'll call it f of t, and notice my x's are labeled y for the vertical and t for the horizontal. And I have some constant a, and then I have an x and an x plus h. Let's let capital A sub f of x represent the integral from a to x of f of t dt. What does that mean? Well, a is an area function. A is giving us the area from a to x underneath this function f. Put that over there. All right. So now I'd like to look at a sub f of x plus h minus a sub f of x. So what would that represent? So let's look at what that's talking about. A sub f of x plus h would give us the area under this curve between a and x plus h. A sub f of x gives me the area just from a to x. So what would the difference be between those two areas? Well, that should give us this area in here. So that's the area that's represented by that. All right, so how could I calculate that area? Well, if I used the left endpoint and made a rectangle, now I'm using the example where this function is increasing from x to x plus h. We could do the same argument if it was decreasing and set up a similar inequality. So I claim that if I take my function, evaluate it at x, and then multiply by h, that'll give me the area of the rectangle with a height of f of x. And that should be less than this area we're talking about, maybe equal to if our function was constant over that short subinterval. So that should be less than a sub f x plus h minus a sub f of x. And that will be less than or equal to the area if I took the rectangle and I defined its height to be the right side of that, which would be f of x plus h, times the width, which would be h. Okay, so that area that I'm talking about, under the curve, between x and x plus h, is going to be somewhere in between these two values, f of x times h and f of x plus h times h. All right, so let's do some calculating here. Let's divide everything by h. H is a positive value, so that won't change our inequalities. All right, now let's take the limit of each of these expressions as h approaches 0. That looks familiar. All right, so let's see. What's the limit as h goes to 0 of f of x? Well, f of x is unaffected by h going to 0, so that's still going to be f of x. What's the limit as h approaches 0 of that quotient? Wait a minute, that should look familiar. That looks like a difference quotient, doesn't it? This is actually the definition of a derivative. That represents the derivative of the function a. And then on the other side here to the right, the limit as h approaches 0 of f of x plus h, well, that's going to be f of x. So notice what we have here. A prime sub f of x is greater than or equal to f of x, and it's less than or equal to f of x. So that's telling us that the derivative of our area function equals f. And now we've made the connection between derivatives and integrals and the area function. So that leads us to the first fundamental theorem of calculus. The derivative of an integral of f of t dt is simply just f of x. So let's look at a few examples and apply this. What's the derivative of the integral from 0 to x of dt over 1 plus t to the fourth? Well, the integrand function here is 1 over 1 plus t to the fourth. So what we just learned was that the derivative of the area function is that integrand function itself. So our answer is simply 1 over 1 plus x to the fourth. How about this one? Well, this doesn't quite fit our theorem. That's a constant there, and then that's a variable x up there. And that's not what we have in this case. So we can use one of our properties of integrals, and we can switch these limits of integration by taking the opposite of the integral. Now we can apply the first fundamental theorem of calculus, and the derivative of that integral will be the function, so 3x plus 1, and then times negative 1. Okay? How are we going to handle something like this? Not quite the same. So what I think I'm going to have to do to make this fit the theorem is use a temporary variable u and let that equal x squared. Then du dx will equal 2x. So now I'm going to try and calculate the derivative with respect to u of the integral from 1 to u of sine of t dt. And by the first fundamental theorem of calculus, that's just going to equal the sine of u. But I don't want du, I want this as a derivative with respect to x. So I'm going to have to multiply that by du dx. And so my final answer is going to wind up being the sine of x squared times the derivative of x squared, which is 2x. So notice, we take this, we plug it in there, but then we also have to differentiate that x squared. And finally, how would we handle this one? Well, this time we don't have a constant down here. So another property of integrals will help me deal with this. Let's split this up into two integrals. Let's make this the integral from x to 0 plus the integral from 0 to 3x to the 4th. 0 is just a random constant that I chose. We could choose any constant. Now the first one, I'm going to have to switch the limits of integration, like the example before. And now I can apply the fundamental theorem of calculus. And for the first one, I'm going to get a negative x minus 2. For the second one, I'm going to get 3x to the 4th minus 2. But then with that chain rule, I'm going to have to multiply that by the derivative of 3x to the 4th, which is 12x cubed. Okay, so let's look at the second fundamental theorem of calculus. This tells us that to evaluate a definite integral from a to b of lowercase f of x dx, I simply need to take any antiderivative of lowercase f, which we'll use uppercase f, which is standard, evaluate it at b minus that same antiderivative evaluated at a. So let's do one example with this. Let's evaluate the integral from 1 to 2 of 4 plus u squared over u cubed du. So first, how about we split this up into two separate fractions. That'll allow us to take the antiderivatives. So the antiderivative of 4u to the negative third is going to be 4 over negative 2u to the negative second. And the antiderivative of 1 over u is the natural log of the absolute value of u. And now we're evaluating these from 1 to 2. So we plug in 2, and we're going to get negative 2 times 1 over 4 plus the natural log of 2 minus, now we'll plug in the 1, and we're going to get negative 2 times 1 to the negative second, which is 1, plus the natural log of 1. The natural log of 1, remember, is 0. So that's going to give us negative 1/2 plus 2 plus natural log of 2 minus 0. So we're going to get 3 halves plus the natural log of 2. Okay, lastly, and we've been running on for a while here, the average value of a function. The average value of a function on a certain interval AB is defined as the integral of that function from A to B divided by B minus A. I think visually will help, a visual picture of this will help you remember. So the integral from A to B of f of x dx is going to give us all this area. Dividing that by the width of the interval, in effect, is asking for us to find a rectangle of the same width that'll have the same area as that represented in the picture. So all we'll do is take the total area divided by the width, and that should give us the height. Let's do one example with this. Find the average value of this function on the interval 1 to 4. Well, let's just go ahead and set it up. We'll do the integral from 1 to 4 of x minus 2 cubed plus 1 dx over 4 minus 1. The antiderivative of that is going to be 1/4 x minus 2 to the 4th plus x, evaluated from 1 to 4, all over 3. So when I plug in 4, I'm going to get 1/4. 4 minus 2 is 2 to the 4th is 16, plus 4, minus, when I plug in 1, I'll get 1/4 times negative 1 to the 4th, which is positive 1, plus 1, all over 3. So that's going to give me 4 plus 4, we have 8, minus 1/4 plus 1 is 5/4, over 3. We have 32/4, minus 5 is 27/4 over 3, so we have 27 over 12. And that reduces down to 9 over 4. And that's how you calculate the average value.